My name is Ali Farid and I'm going to explain example 10.6. In this example we have extension spring made from a hard drawn steel wire. The wire diameter is 0.9 mm, outside coil diameter is 6.3 mm, the hook radius is 2.7 mm, and the radius of connection of hook to the body is 2.3 mm. The initial tension is 5 Newton. The number of body coils is 12.17. And by using this given information, we have to first determine the physical parameters of the spring. The first physical parameter that I'm going to find is mean diameter. And as you know, mean diameter is outer diameter minus wire diameter. So 6.3 minus 0.9 is 5.4 millimeter. The second physical parameter is a spring index, which is mean diameter over wire diameter. So 5.4 divided by 0.9, spring index is 6. The third physical parameter is curvature factor Kb, and it can be find similar compression spring. So by using this equation, we will substitute C into this equation and Kb is 1.24. The next parameter is number of active coil. As we explained in lecture, in extension spring, hooks also affect on the deflection, and we have to find the equivalent number of active coil. An equivalent number of active coil can be found by equation 1040. By using this equation, we need first find parameter G and E. So we have to refer table 10.5 to find parameter G and E for hard drawn wire, which they are equal to 79 and 198 respectively. So the number of active coil is 12.57 turns. In next physical parameter, we have to find the spring rate, K, and it will be found similar to compression spring by using this equation. So we will substitute the number of active coil into this equation. And again, we should not forget that to use millimeter in this equation, and here should be megapascal, so the result is Newton per millimeter. So the spring rate is 3.27 Newton per millimeter. The next parameter is free length, and it can be found by using equation 39. So we have to substitute C and B and wire diameter to find free length of the extension spring, which is equal to 20.9 millimeter. Now I want to know how much over a spring will be deflect if I apply 23 Newton. I'm using 23 Newton because it's given in part C, which says find the factor of safety under a static load of 23 Newton. I'm still doing part 1, but now I want to find how much is the deflection under this load, which is 23 Newton. As we explained earlier again in the lecture, the initial load is necessary to be applied on a spring to maintain its free length, and this initial tension is in reverse direction with the applied load. Due to this reason, we deduct the initial tension from the applied load because they are in the reverse direction. That's why here the sign is negative. Okay, so we will find the applied load minus tension load divided by a spring rate. It gives us the deflection. So the spring will be deflect 5.5 millimeter if we apply 23 Newton. So the free length plus the deflection length give us the length of a spring after applying this 33 Newton load. So when we apply this 23 Newton load, the length of a spring will be 26.4 millimeter. In part B, we have to check the initial preload stress condition. Again, I will refer to this slide. We mentioned earlier that initial load always should fall in this range. So I have to substitute C into this equation to find the range of initial stress. But the thing that we have to notice here, this equation is for American units and we have to convert it to metric. The equation for metric unit can be used, we can use this equation. The only difference is the constant here, which is 231. So when we substitute C into this equation, we will find that initial tension should fall in this range. That means between 98.6 megapascal to 147. Now let me find how much is the initial stress. The initial load was 5 Newton. So I have to use the compression spring equation to find the tension. But in this case, I'm not going to substitute KB here. If you remember, there was a KB always here for compression spring. But for initial tension, we shouldn't use this KB at the equation, because the preferred range also has been found without considering this curvature factor correction. So I will substitute 5 Newton, which is the initial tension, into this equation, and I will find that the initial tension is 94.3 megapascal. As you can see here in the textbook said that the initial tension of 94.3 is in the preferred range. That means this should fall in this range, but actually it's not. It's out of the range. The difference of your textbook and what is happening really here is, I think, due to the convert of American units to metric units. But as you can see, 94 is almost close to 94 is almost close to 98. So I think this is out of range because the textbook has already converted to metric units, and the problem is coming from that side. Okay, in part C, we are required to find the factor of safety under a static 23 Newton load. Okay, in order to determine the safety factor of extension spring, we have to notice that in any extension spring, there is 3 critical locations. And we have to study about these 3 critical locations. One of the critical locations is the coil body, and the shear stress in the coil body has to be found exactly similar compression spring. So we have to use compression spring to find shear stress in the body of the spring. Another critical location is at location A, here, the location which will experience bending in the extension spring. In order to find this bending stress, we need to find C1, which is function of R1. R1 is the radius of the hook. So I have to replace the radius of the hook into this equation to find C1, and C1 should substitute into this correction factor. And later on, correction factor will be substituted into this equation to find the bending stress. The next critical location is location B. That means the place that hook is connected to the body of the extension spring. And R2 is the radius of the connection of hook to the body. So R2 is the radius of location of connection hook to the body. And we have to find C2 and then KB. Then we can find the shear stress at this location. So we have shear stress at location B and bending stress at location A. So it's different type of stress at these two locations. Okay. Before I find the shear stress and bending stress at this location, first I need to find the ultimate strength of the material. So I need to find factor parameter A and M from table 10.4. For the hard-drawn material, A is 1783 and M is 0.190. So the ultimate strength is 1819 megapascal. Okay. Now here we have to refer to table 10.7 to notice an important issue. For this group of materials, the torsional and bending stress, the torsional and bending yield strengths are a percentage of the ultimate strength. For example, in case of the body of the spring which is under torsion, the torsional yield strength is 45 to 50% of ultimate strength. So as we had similar to compression spring, we can say that the yield strength is 45% of ultimate strength. So 45% of 1819 megapascal equals to 818.6 megapascal. So this is the torsional yield strength of body. Now I have to find the shear stress in the body. So the equation is exactly what we had in compression spring, and earlier we found Kb. In part A we found Kb. So I will substitute Kb into this equation and we are going to find safety factor under 23 Newton load. So shear stress under this 23 Newton in the body of the spring is 538 megapascal. Now I can find safety factor in the body of the spring, torsional yield strength divided by the shear stress, 1.72. So this is safety factor at the body of the spring. I can write NB to illustrate the safety factor in body of spring. As I mentioned earlier, another critical location is here at location A. So R1, the radius of this hook, should be substituted here to find C1, and then we will find Ka, the correction factor at location A, by using this equation, which is 1.14. Now I can find again the bending stress. This is the bending stress at location A. So by applied load 23 Newton Ka that I found here, I can find the bending stress, which is equal to 1025 megapascal. Again, I need to refer to table 10.7. How much is the axial yield strength in the hook of the spring? The bending stress, the bending yield strength or axial yield strength is 55% of the ultimate strength. So you write that the axial yield strength is 75% of ultimate strength, which is equal to 1364 megapascal. Now I can find the safety factor at location A, which is yield strength divided by bending stress, so 1.33. The third critical location is the connection of the hook to the body of the spring. That means somewhere here. So the radius of this connection is R2 2.3, so C2 is 5.1. Now I have to find the correction factor for this location, but you have to notice here that this Kb is different with the curvature factor in the body. That's why we differentiate this Kb by using these two parentheses. So this Kb without parentheses indicate the correction factor in the body of the spring, and Kb with these two parentheses shows the correction factor at the location of connection of hook to the body. And therefore we can find Kb, which is 1 point. We can find the shear stress at this location B by substituting Kb into this equation, similar what we had in compression spring. And therefore the shear stress at location B is 511 megapascal. Now again I need to refer to table 10.7 to find out that how much is the torsional yield strength at this location B, here mentioned at the end. End means end of the body spring. That means the location that end of the body of the spring connected to the hook. So the torsional yield strength is 40% of the ultimate strength. That means I can write that SSY at location B is 40% of ultimate strength. I use this parenthesis and B to differentiate with torsional yield strength in the body of the spring. So the safety factor at location B is 1.42. At this stage, I have to compare the safety factor in the body, safety factor at location A, and safety factor at location B. Safety factor at body was equal to 1.52 at location A was 1.33, location B 1.42. So if we compare these three safety factors, you can see that safety factor at location A is smallest compared to others. So if your spring preloaded by any load greater than the allowable load, the failure in the spring will happen at location A. So here said yield due to bending of the end hook will occur first. Okay, so the most critical location is location A with lowest safety factor. So we have to consider this location to design our spring. Okay, this is end of example 10.6. Thank you.